Hello everyone, my name is Amrita Bhatnagar. I am from the CSE department of Akgec. Today I am going to explain a very good topic, process and its states of the operating system. So these are the main outlines of the lecture. Firstly, we will discuss about the processes, what is a process and how it works. Then second one is the process structure. Third one is the process states. Then we will see what is the state transition diagram of the processes. Then we will discuss process control block, and then after that we will discuss about the context switching. So firstly we will see what is process. A process is a program in execution. Process execution must progress in sequential fashion. A program is a passive entity, but a process is an active entity. A program becomes a process when an executable file is loaded into memory. A system consists of collection of processes. All these processes can execute concurrently with the CPU by switching the CPU between the process. Hence, the CPU utilization increase. So that we can say that if a program is written and stored in the memory, then when we load this program into the memory and execute it with the help of CPU, then it becomes process. So we can say that a program which is in the execution is known as a process, and these processes have multiple stages also. Now you can see here, when we talk about the structure of the process, then we have these multiple entities in the process structure: program counter, stack, data section and heap. So we will discuss these points. Now first one is the text section. Text section means it comprises of compiled program code read in from the non-volatile storage when the program is launched. It also includes the current activities as represented by the value of the program counter and the contents of the process register. Then the second part is the data section. Data section stores the global and static variables allocated and initialized prior to the executing main. Now, the third one is the heap. The heap is used for the dynamic memory allocation. Dynamic memory allocation means the memory allocation at the time of running the program is managed via calls to new, delete, malloc and free, etc. The stack is used for local variables. Space on the stack is reserved for local variables. So fourth one is the stack, and stack is mainly used when we execute a particular function. When we call a function, then what happens? The particular parameters related to the functions and some return addresses are stored in the stack. Fine. Then what happened? When the this function is completely executed, then again the stack will be empty. So this is the main use of the stack. So this is the another section of the process. So we can say that the space is freed up when the variable go out of the scope. So that stack can be used when the function is executing, and when the function is completely executed, then stack will be empty. Now you can see this is the diagram for the process. You can see here stack, heap, data and text. This is the main section of the process. You can say that process is divided in these four sections. Main sections are these. Now process states. Now this process have multiple status of also. First one is the new. New, when the process is in the stage of being created. When the process is created, then it will be in the new state. Second, ready. The process has all resources available that it needs to run, but the CPU is not currently working on this process instruction. For example, a process is executing, then it requires multiple resources, and if the resources are available at that time, then it is on in the ready state. After the ready state, it will go into the running state. The CPU is working on this process instruction. When the process in the running state, what it means? CPU is working on this process. Fourth one is the waiting. The process cannot run at the moment because it is waiting for the some resources. For example, if a particular process don't have any resources and it cannot be complete without that resource, then it will be in the waiting state. The process will wait for the particular resource, and when the process get this resource, then it will be in the ready state. And if the process will not get the resource, that up to that time it will be in the waiting state. So last one is the terminated. The process has completed. When the process will complete it, the final state will be the terminated state. Now we can see the diagram. You can see here, this is the diagram for the particular process. So first one is the new state. New is when the process will be created. Then the state of the process will be new. Then next one is the ready. When we give all the resources to the process, and process is ready to execution. For the execution, then it will be in the ready state. After the ready state, it will go to the running state. Running state means when CPU is allocated to the process. In the ready state, it have all the resources, but CPU is not allocated to the process. But when it is in the running state, the process will be allocated to the CPU. And the last one is the terminated. So this is the next state. But if there is any IO request between the running state, when the process is in the running state and it will have a particular IO request, then it has to wait for the IO. So it will go to the waiting state. This is another state. And after that waiting state, when the resource is available for the process, then it will again go to the ready state, and then it will go to the running state again. So this is the process, and there will be possibility the process will have a particular interrupt. If the process will have particular interrupt, then again process will go to the ready state. Fine. So these all are the major 5 states, and here there is a major role of scheduler. In the next slide, in the other slides, we will see what is the role of scheduler in the state transition. CPU, what is CPU scheduler? Whenever the CPU becomes idle, the operating system must select one of the processes in the ready queue to be executed. The selection process is carried out by the short-term scheduler or CPU scheduler. The scheduler selects a process from the processes in memory that are ready to execute and allocates the CPU to that process. The records in the queues are generally process control blocks of the processes. So CPU scheduler is that scheduler which is also known as a short-term scheduler, which select a particular process from the memory to give to the or to allocate the CPU. Now we can have more than one type of schedulers. First is the short-term scheduler, where in operating system, the short-term scheduler, also known as the CPU scheduler, which we have already discussed, decide which process in the ready queue to execute next and allocates the CPU to it. It makes this decision frequently, often triggered by events like clock interrupts or IO completion. The short-term scheduler uses various scheduling algorithms to determine which process to execute next, such as first come first serve, shortest job first, round robin, and priority based scheduling. This is the main use of short term scheduler to allocate the particular process to the CPU from the ready queue. Next one is the long term scheduler. Long term schedulers, also known as a job scheduler, which decide which process to load into the memory from secondary storage. So this is a main use of long term scheduler. And third one is the medium term scheduler. Medium term scheduler handles the swapping process in and out of the memory to manage memory uses. So these are the main 3 type of schedulers which is used in the process stage transition, or we can say that all the process execution. Now the next is process control block. A process control block is a data structure used by the computer operating systems to store all the information about a process. It is also known as a process descriptor. When a process is created, initialized, or installed, the operating system creates a corresponding process control block. For each process, there is a process control block which store the following type of information. So we can say that PCB or process control block is a information related to the process. So when the process is created, then a PCB also created with the process, and PCB we will have the all the necessary information related to the process, and this information is keep in the a particular block, and is this information is known as a process control block. So you can see these all are the different type of information which keep kept by the process control block. First one is the process state. What it means, process can be in a running state, waiting state, ready, new, or terminated. So it will tell about the process is in the a particular state. For example, it is in the waiting state. Process ID, when the process is generated or created, then a unique ID is allocated to the process, which is known as a process ID. So that this parent process ID or process ID is also kept by the process control block. CPU register and program counter, these need to be saved and restored when swapping process in and out of the CPU. CPU scheduling information such as priority information, pointers to scheduling queues, because we have multiple type of or different type of CPU scheduling algorithms. So we can use any type of scheduling algorithm. So the information related to the CPU scheduling can be mentioned in the CPU scheduling information, and it can have the other type of information related to pointers and priority informations. Memory management information, it can have page tables, segment tables, base register, and limit register. These all are the related to the memory management. Accounting information, user and kernel CPU time consumed, account numbers, limits. So these all are the accounting information. For example, a particular process, how much time is taking, CPU time is taking, and what is the account number, what is the limit, and these all are the information related to the accounting information which is stored in the accounting information. IO status information, device allocated, open file, tables, these all are the input output status information which is kept in the process control block. So you can see this is a diagram from the process control block, which can have these different type of information: process state, process number, program counter, register, memory limits, list of open files. So these all information is known as a process control block. So we can say that this is the information related to the process which is required later on. Next is the context switching. So when we have multiple processes in our memory, then there is a need of a context switching, because when the particular process is executing, there is a possibility we have some input output operations in the process. When this process will go for the input output operation, then there is a need to give the another process to the processor, because otherwise the processor will be idle. So this is the process known as a context switching, when the one process is deallocated to the processor, and another process is allocated to the processor, then it is known as a context switching. Context switching is a process that involves switching the CPU from one process or task to another. In this phenomena, the execution of the process that is present in the running state is suspended by the kernel, and another process that is present in the ready state is executed by the CPU. So with that, when we are using multiple or multi-programming, then context switching is required. Multi-programming or multi-sharing, then this context switching is very much required. It is one of the essential feature of the multitasking operating system. The processes are switched so fastly that it gives an illusion to the user that all the processes are being executed at the same time. So user cannot recognize these switching are already are being done in the system. So you can see this is the example of context switching. You can see here we have two processes, P0 and P1 process. So these processes are in the memory. So firstly, we can see here P0 is executing in the initial state. So that you can see here this is the executing. When the context switching will start, the all the information related to the process P0 will be saved in this process control block. So because this process is not completed, now we are doing what we are doing here. We are doing here switching, CPU switching. So process P0, some part of the process P0 is executed, and now we are saving the information related to the P0 into the PCB0 block. Then after that we will, because now we have to execute the process P1 now. So this is known as a context switching. Firstly, we are executing the we were executing the P0. Now we are executing the P1. So we will reload the value or information related to the PCB1. This is the process control block of P1. So we will reload the PCB1 and we will start the execution of the P1. So you can see here, this is the it is showing the execution of P1 here. Now again context switching will be done. Then what will happen? All the information related to the P1 process will be stored in the PCB1, so that we can later on use it. So okay. Now after that we will again, because we will again execute the process P0, so that again the information related to the PCB0 or process P0 will be reload, and again the P0 process will be executed. So that this is known as a context. Firstly, we will execute P0, then CPU will switch to the P1, then again P0. So this is known as a context switching. So when we are using time sharing system or multi-programming system or multitasking system, then this CPU scheduling is required, or sorry, CPU context switching is required, very much required. Okay, thank you.